let's talk about electron configurations and orbital diagrams. So I already did a lesson introducing electron configurations, which comes after my lesson on atomic orbitals and quantum numbers. So these lessons are all in sequence, but now we're going to expand on the electron configurations, build into the orbital diagrams. We're going to do the noble gas shortcut and talk about a couple of interesting scenarios. Okay, so let's jump in now. So let's just start off with doing the noble gas shortcut here. And so the idea is, if we look at the periodic table, group 8A over here, which is, remember, the groups of columns, these are the noble gases. And so their valence shell, which is the outermost shell of electrons, is always full, because they're all the way over here at the P6, right? So this would be S1, S2, depending on what row we're in, and then this all the way at the end would be P6. So the S and P sublevels are always completely full for the noble gases. Of course, helium only has the 1s, so 1s2, but that is still, shell 1 is full there. So what we can do is we can always take, for a larger element, the noble gas that precedes it, and just show that basically this element is going to have the same configuration as that noble gas, plus some extra stuff. So let's do a quick example. Let's look at, let's just do sulfur, okay? So if we look at sulfur, I'm going to use this notation here. Z is equal to, so the Z is the atomic number, right? And it's 16. And remember that Z, being the atomic number, is equal to the number of protons. And if it's neutral, that's also the number of electrons, okay? So I'm just going to be doing this for neutral elements for the moment. But let's get the electron configuration of this the way that I taught you in the last lesson. And so in order to get to sulfur, we have to go through everything that precedes it. So it's going to be, this is period 1. This is the S block. I have to go through both positions. So 1s2, 1s2. I have to go through the whole second period. That's the 2. This is the S. I have to go through both spots, 2s2 and 2p all the way through 6. So we have 2s2 and 2p6. And then we have 3s2 and 3p, 1, 2, 3, 4. It's the fourth one. So 3s2, 3p4, okay? So now, that's just the full electron configuration, right? So now let's look at what the noble gas shortcut would be. So the noble gas that precedes sulfur is neon, right? So just go up and then all the way to the right, that's the noble gas. And so neon is 1s2, 2s2, 2p6. So this whole area here, from the 1s all the way over to the 2p6, that just is the electron configuration of neon. And so instead of having to write it out, because each next element is going to have the same electron configuration, but just add another electron into it. And so as a shorthand notation, instead of writing that, we could just write that noble gas, neon, we put it in brackets, and then we just write the valence shell electron configuration, meaning the outermost shell, which is shell 3 in this case. So we have the 3s2 and 3p4. So writing out the full electron configuration of this, or this noble gas shortcut, is saying the same thing. This is just a shorthand, okay? So now that we understand that, let's now look at doing orbital diagrams. And so the idea is, I'm not going to do it for the internal, the noble gas core here. I'm just going to do it for the valence shell. And a box represents an orbital. And so if we went back to my analogy that I taught in the other ones, where orbitals are like the bedrooms in the apartments of an apartment building, right? So remember that the S's only have one orbital. So that's just going to become a box. And I'm just going to label this 3s. And then the P sublevels have 3 orbitals, right? And as I mentioned, if you remember the 4 sublevels that we're concerned with, it's SPDF. So it's like save the PDF file, SPDF. And the number of orbitals are just the first few odd numbers, 1, 3, 5, and 7. So that's really easy to remember. So that's the S. And then any P sublevel, doesn't matter what shell it's in, is always going to have 3 orbitals. And we just draw a longer box and then we divide it into 3. And so, and then we're just labeling, what is this box? That's the 3s orbital, right? And then these are the 3 orbitals of the 3p. Sometimes people will put like the px, the py, and the pz. That's one way to do it. This is also fine. So now we have to draw the electrons where they go. And so for the 3s, there's only 2 electrons in it. And remember, you can't have 2 electrons with the same spin in the same orbital. They have different spin directions. And so I did talk about this in my quantum numbers video. But I'm just restating it now. You can't have like 2 up spin electrons. You have to have 1 up and 1 down. And the idea is that they have a magnetic field associated with them. And so basically it's kind of like having 2 magnets next to each other, and you're not going to have the north to north and south to south facing each other. They're going to flip. So it's the north side of one and the south side of the other are next to each other. So there's like a more of an attraction than that complete repulsion. Okay. That's kind of the idea. And so when we fill this in, we have to have an upspin electron and a downspin electron. And we do these half-headed arrows. And the idea is that the half-headed arrow represents 1 electron. So that's that. So now in the 3p, now we have several orbitals here. What you always do is you put 1 electron in each orbital, all facing the same direction first, and then you double up, okay? So in other words, I'm going to start, and the convention is you typically put them all up. You could put them all down, but the point is they all have to face the same direction. And it's just normal to just always start going up, and it's just good to have, just always do the same thing, right? But we're going to go here. That's 1, 2, 3 electrons. And the idea being electrons are negative. Negative charges repel each other, right? And so they're all going to get their own individual orbital to buzz around in, right? To exist in, I should say better. And this, if we go back to my analogy, it's like, hey, if you have a 3-bedroom apartment and you got 3 people, well, you're all going to want to spread out and have your own room, right? So now that would be 3p3. That's what that would look like. And you want them all spinning in the same direction. So I'm not going to change one of these arrows to face down. That would violate some rules here. So they're all going to face the same direction, but we have a 4th electron. So we have to double up somewhere. And it doesn't really matter. You could just double up in any of these as long as it has the opposite spin. But again, in convention, we're typically just going to go back to the first box and just stick it in there. But I could put it a down spin in any of these other ones. But I'm just going to keep things looking pretty typical. And there we go. So this would be the orbital diagram and of the valence shell of sulfur. This is the noble gas shortcut of the electron configuration, and then this is just the full electron configuration. So now let's do another example that gets a little funky, I suppose. So I also mentioned in my last video that some of the larger sublevels, like the D and the F, they like to be either completely full or half full. It's more stable. And so let's look at some interesting scenarios that happen in the D sublevels there. Typically in the general chemistry course, you're not going to be doing electron configurations of stuff with the F orbitals and having to figure out, you know, if you're going to, how to move your electrons around. So let's get into this. So let's do something like chromium. That's a good one to do. So when we did calcium last time, I showed how we skipped the 3D after, if we run the calcium, if I do the noble gas shortcut here, it would be the electron configuration of argon followed by the 4s2. So in other words, this is period 3, and I'm not putting any electrons in the 3D sublevel because the 3D actually gets filled up after the 4s, right? But now for elements in this area, after we get through the 4s, then we start filling up the 3D. And again, I cover this in my last video just on electron configuration, so you can check that out. So now let's do chromium. So chromium is Z equals 24. And let's do the noble gas electron configuration for that. So the noble gas before it is argon. So we do brackets and argon. And of course, I could have written out 1s2, 2s2, 2p6, 3s2, 3p6, and that's the same as argon. But now, after argon, we get the 4s2, 4s2, and then we have the 3d, 1, 2, 3, 4. And I'm just writing this out like this for the moment. 3d4. Now, this is not going to be our final answer. So if anyone already knows how this goes, just bear with me. This is what we would get by just doing our electron configuration by looking at the periodic table. But now let's look at the orbital diagram. And so we have the noble gas core, which everything is just completely full under there. But then we have the 4s, so let's draw a box for that. That's the 4s. And let's do the 3d. And remember that the d sublevels have 5 orbitals. So I'm going to draw a long box. I think that's about 5 wide, right? So let's see, we're going to do, that's 1, 2, 3, and then 4, 5. Not bad. All right, so that's our 3D. I'm impressed with my box drawing skills. That's really sad. So let's go ahead now and fill these up. So if we just follow the way that we did the electron configuration, just by reading it off the periodic table using that method, what we would have is 1 up, 1 down, because there's 2 electrons in there. And then in the 3D, we do 1 electron in each orbital until we have to double up, right? So it would be 1, 2, 3, 4, right? But I mentioned last time and just before that the larger sublevels, like a D or an F, are more stable when they're either half full or completely full, okay? And so what actually happens in this circumstance here is it'll be more stable, lower energy, for one of these electrons from the 4s to actually jump into the 3d. And then this is half full, and this is half full. And that gives you a more stable electron configuration. So you're going to notice that for elements that are almost half full of the D, it's like a D4, they're going to snatch an electron from that S that just preceded it and throw it in. And the same thing is going to happen if you are almost completely full. So if you had like 3D9, well, it can actually snatch one of the electrons out of the 4s and throw it in so that you get 3D10, 4s1. All right, guys? So over here, I kind of got ahead of myself. Over here, what I want to show is we're going to move this electron. It's not going to be here anymore. And it's going to jump over here. And so then this is actually not correct. Now, you don't have to draw out the orbital diagram to figure this out. Once you've seen it, you can just kind of think, okay, yeah, D has 5 orbitals. So then a D4 or a D9 is going to want to be either a D5 or a D10, right? And just remember, this superscript is just the number of electrons in that sublevel. So what we're really going to do, we're going to correct this, and we are going to do 4s1 and 3d5. And now that is the actual electron configuration of chromium. All right, guys? So now it gets even stranger when you start bringing the F's involved, and it's a little harder to just predict the electron configurations based off of these kind of like simple sort of rules. But just remember, there's really, you're only going to see this once in a while, like I said, like chromium and those elements, or like copper and those elements. If it's going to be either, if it would have ended in a D4 or a D9, you're going to take one from the S and make it that the D is either half full, so you have this, so you're going to end up with an S1 and a D5, or if this was D9, it would rather be completely full. So you would make an S1 and a D10. All right, guys? So drop any comments if you have any questions or if there's other topics you guys want to see. And also, if these videos help you, please give a like, follow, share, save it so you can review it again later. And if you'd like to continue, go above and beyond, you can patronize me over here. That helps me to continue making these for free. All right, guys, thanks again, and I'll see you in the next one.